In this video, we're going to discuss the cross product of two vectors. Taking the cross product is one of the ways of combining two vectors, and specifically, it is the way of combining two vectors to arrive at a third vector which is perpendicular to both of the original vectors. So to begin with, what we're going to do is we're going to talk about how we could identify the direction of some C vector, which is perpendicular to both vectors A and B. As an example of finding the direction of the cross product of two vectors, let's look at a vector A which points directly in the x direction and a vector B that points directly in the y direction. Now, if we let the C vector equal A vector cross B vector, the C vector must point in the z direction because this is the only direction for which the C vector makes a 90-degree angle with both the A vector and the B vector. Now, we have a slight problem in that there are actually two vectors which satisfy our condition of being perpendicular to both A vector and B vector. The vector C, which points in the positive z direction, but also the vector D, which points in the negative z direction. It also makes a 90-degree angle with each of these and therefore has satisfied all of the requirements that I have so far stated. Now, because we would like to have a unique answer, that is, we want only one vector which points in one direction as the answer to our cross product, we need to develop a convention for whether we choose vector C or vector D. And the convention that we are going to use is called the right-hand rule. Using the right-hand rule requires that we make our right hand specifically, into a very specific shape, with the index finger pointing straight ahead, the other three fingers at a 90-degree angle to the index finger, and then with the thumb pointing straight up. And you can kind of see how your index finger, your other fingers, and your thumb are all at 90-degree angles from one another. Now, what we want to do is take this hand position and align it with the vectors in our cross product. The first step with aligning our right hand with the cross product vectors is to take the first vector, in this case that is A vector, and align our index finger with that vector. So your index finger should always point in the direction of whatever the first vector in your cross product is. The second vector in your cross product should be pointed in the same direction as your other three fingers. In this case, the second vector in our cross product is the B vector, so our three other fingers need to point in the direction of the B vector. In this case, that is the y direction. And finally, our thumb is going to point in the direction of the result of our cross product, our C vector. By aligning our right hand in this way, we can see that the result of the cross product must point in the positive z direction in this case, and not in the negative z direction. So the D vector, though it satisfied our rule about the 90-degree angles, making a 90-degree angle with both A vector and B vector, it does not satisfy our right-hand rule requirement, and so only C vector is the result, has the correct direction to be the cross product of A and B vectors. In order to see how this works in more detail, let's try a few other examples. As another example of using the right-hand rule to find the direction of the resulting vector when two vectors are cross product, let's look at the vectors A and C. Vector A points in the positive x direction, vector C points in the positive z direction, and if we use the same hand position, our index finger should be pointing directly to the right, our other three fingers should be pointing directly upward toward the top of the screen, and therefore our thumb should be pointing straight out of the screen towards us. This leads us to believe that the resultant vector of A cross C should be pointing in the negative y direction, that is out of the computer screen in our coordinate system. We can also see that the F vector satisfies our initial requirement of being both perpendicular to A and C by noting that it makes a 90-degree angle with both of those vectors. As a final example of using the right-hand rule, let's consider a vector A that points in the positive x direction and a vector L that points in the negative z direction. In order to analyze this, we need to place our hand such that our index finger is pointing to the right in the direction of A. Our other three fingers are pointing down in the direction of L, which leaves our thumb pointing toward the computer screen, which is also the positive y direction in our coordinate system. We can see that this M vector also makes a 90-degree angle with our original two vectors A and L. Now that we've seen how to find the direction of a cross product using the right-hand rule, let's learn how to mathematically calculate the magnitude and direction of the vector that results from a cross product. In order to do this, I've written down two arbitrary vectors in 3 dimensions. They each have some x, y, and z component. I've also written down a matrix in which the top row of that matrix is the unit vectors in each direction, I hat, j hat, and k hat, and the second row is our A components, and the third row is our B components. And what we're going to do is we are going to take the determinant of this matrix. Now, the determinant is an operation that you can do on a matrix. And if you haven't seen this before, we are going to learn how to take the determinant of a matrix right now. So the easiest way to take the determinant of a 3x3 matrix like this is to actually write the matrix out 3 times, and you're going to get a component of your determinant from each of these 3 matrices. So the first matrix here, what we're going to do is we are going to circle the I hat component, and that is going to get multiplied by the determinant of the submatrix created by crossing out the row and column in which the I hat is located. So we're going to take I hat and multiply it by the determinant of this submatrix. And the way that we take the determinant of a 2x2 matrix is that we multiply the diagonal rows here. So we multiply these two together. That is AY times BZ. And then we subtract these two components together. That is minus AZ multiplied by BY. So our first of our 3 matrices gives us the I hat component of the result of our cross product. Now we can move on to the second matrix, and this time we're going to think about the j hat component. We're again going to cross out the row and column associated with our j hat, and we're going to take the determinant of the matrix formed by the not crossed out components. Now, when you take determinants this way, the first component, the I hat, is positive. The middle component is going to be negative. So we're going to subtract the j hat. So we're going to say minus j hat, and we're going to do exactly the same thing that we did for the I hat. That is, we're going to multiply these two components AX multiplied by BZ. And then we are going to subtract from that the other diagonal minus AZ times BX. And finally, we are going to take our K hat component. We are going to cross out the row and column associated with the K hat component. And we are going to take the determinant of the submatrix of the left behind components. The K hat component is positive, so we are going to add K hat, and we're going to multiply it by exactly the same way that we've done with the other matrices. That is, AX times BY is going to be the positive component. So AX times BY, and then the negative component is going to be AY times BX. So then I'm going to subtract AY times BX. So whenever you write this out, it's always going to be that the I hat component has a positive sign in front of it when you write it out here. The J hat component has a negative sign, and the K hat component, again, has a positive sign. You can even write above your matrices this plus minus plus convention. Another thing to note is that the I hat component contains only Y and Z components of the A and B vectors. Likewise, the J hat contains only X and Z components of A and B vector, and likewise for K hat. So the I hat component depends only on Y and Z in your original vectors. The J hat component of your resulting vector depends only on the X and Z hat components of your original vectors. And the K hat component of your resulting vector depends only on the X and Y components of your original vector. Now that we know the general process of taking the cross product of two vectors, let's try it on two actual vectors. So I've just created two arbitrary vectors, A and B, which have some components in the X, Y, and Z directions. And I have placed their components into the matrix as we just showed. So AX is 3, so that goes into the first column in the second row there. Likewise, AY is -4, so that goes into the center of the matrix. So now what we can do is we can find the I, J, and K hat components of our cross product by taking the subdeterminants of the three matrices as we just did. So first we'll start with the I hat component, which remember has a positive sign. So we're going to have a positive I hat multiplied by the submatrix created by crossing out the row and column in which the I hat is located, and that comes out to this submatrix here. And just like we did before, we're going to multiply the upper left and bottom right, and then subtract the multiplication of the top right and bottom left. So that gives me -4 times -5 is 20, minus 2 times 0 is 0. So that is the I hat component of my cross product. I can now move on to the second matrix, using the J hat component, which it has a minus sign, so I'm going to subtract J hat, multiplied by the determinant of the submatrix created when I cross out the associated row and column. And again, I multiply the bottom right and top left, and then subtract the multiplication of the top right and bottom left. So this leads to -15, 3 times -5, minus -7 times 0 is again 0. And finally, we get to our final component, the k-hat component, which is positive again. We are going to cross out the row and column associated with k-hat and find the determinant of the submatrix that is left behind, which is going to be plus k-hat multiplied by our set of components subtracted from one another. So we have 3 times 2 is going to be 6, minus negative 4 times negative 7 is a positive 28 that we are subtracting out. Simplifying this down, I get 20 I hat plus 15 j hat minus 22 k hat as my final answer. So this is the final result of the vector A crossed with B. Now, it's a bit difficult to determine whether this matrix or whether this vector that we have found is in fact perpendicular to both A and B, because it's hard to visualize these vectors in 3 dimensions and really know whether they would be perpendicular or not. In order to solve this problem of being able to check if our vectors really are perpendicular to one another, we actually can use the other way that we know to combine vectors, which is the dot product. So if you remember, if I take the dot product of 2 random vectors, I'll say vector u dotted with vector v, this is equal to the magnitude of u multiplied by the magnitude of v multiplied by the cosine of the angle between them. Put in my magnitudes. And remember that if this angle theta is 90 degrees, then the cosine of theta is 0, and the dot product of my 2 vectors is 0. So this means that if the dot product of 2 vectors is 0, they must make a 90-degree angle with one another and therefore be perpendicular. So what we would expect is that if we took C dot A, that would be 0, and we would also expect that C dot B would be 0. If this is true, then C is truly perpendicular to both A and B. So let's check. Well, C dot A, remember when we take a dot product, we multiply the I hat components by the I hat components, adding the j hat components multiplied by the j hat components, and then adding the k hat components multiplied by the k hat component. So for C dot A, we get 3 times 20 minus 4 times 15 minus 0 times 22, which leads to 60 minus 60, which is 0, as expected. So C is perpendicular to A because the dot product of C with A is 0. We can check the same thing for C dot B. In this case, we will find that we get negative 7 times 20 plus 2 times 15 plus 5 times 22. And if you plug all of this into your calculator, you will again find that it in fact equals 0, as we expect. So we found that C is perpendicular to both A and B. As a final example of calculating the cross product, let's look at one of the first examples that we did when we were learning how to use the right-hand rule to find the direction of a cross product. So we have a vector A, which points only in the x direction, and a vector C that points only in the z direction. And we can write A vector as 1 I hat plus 0 j hat plus 0 k hat. So we have given A length of 1. And we can write the vector C as 0 I hat plus 0 j hat plus 1 k hat. If you're ever given a vector that has components in, say, only one or two directions, just insert a 0 for that third direction so that you have 3 components to plug into your matrix. So in this case, our matrix has a second row of 1, 0, 0 and a third row of 0, 0, 1 for A cross C. Now we can use our same determinant calculation in order to calculate the dot product or the cross product of A cross C. And what we find is that F vector, the result of A cross C, points in the negative j hat, the negative y direction, just as we would expect from the right-hand rule. So this is just an example of how the right-hand rule and our mathematical formulation give the same answer in terms of the direction of our cross product. Now, the right-hand rule would not give us the length of the f vector. The only way to get the length of that f vector is to actually calculate out the cross product mathematically. But at least we see that the direction from the right-hand rule and our mathematical direction line up with one another.